Hi everyone, I hope you are doing well. In this video, I'm gonna talk about music algorithm. Music is one of the most important algorithms in signal processing, especially in spectral analysis. For example, for sinusoidal frequency estimation and for direction finding or direction of arrival estimation. So it's really worth talking about this algorithm. The word music stands for multiple signal classification. It's based on eigenanalysis of correlation metrics. In scenarios like when we have an sinusoidal signals in noise or in an array, in a uniform linear array, we have n sources and signal sources, and we want to find the angle of arrival. We can form correlation metrics or covariance metrics as R equals to A P A Hermitian plus sigma 2 I. I is an identity matrix. This is because we consider white noise, and this is related to the signal sources. A is a Vandermonde matrix. R is M by M matrix. A is M by N matrix. P is N by N matrix. And H stands for conjugate transpose. The number of sources and the number of frequencies is N, and the structure of A is like this. A is a matrix, and the columns are like this. Omega 1, omega 2, and omega n are frequencies which should be estimated, and actually we have the estimate of R based on the observations, and we should estimate frequencies. In uniform linear array frequency, we call this spatial frequency equals to theta is DOA, direction of arrival of signal, and omega is spatial frequency. So if we can estimate this frequency, we can estimate DOAs. And in the case of temporal signal, and when we have n frequencies and sinusoidal signal, we can estimate the frequency. Okay, A omega is 1, Because we have different frequencies in this column, the columns are independent, are linearly independent, so the rank of A is n. If we discuss about the rank of this matrix, A has rank of n, P is a diagonal matrix, and the entries are the power of signals alpha 1, 2 and alpha n 2. It's n by n matrix, so the rank of P is also n. A Hermitian is also having the rank of n. So the rank of AP Hermitian is n. But because of the noise, because the diagonal matrix, the rank of matrix A R is M. APA Hermitian is a M by M matrix. Is an M by M matrix, but the rank of this matrix is n. This means we have n non-zero eigenvalues and m minus n zero eigenvalues, like lambda 1 tilde, lambda 2 tilde, lambda n tilde, and others are 0, because the rank of the matrix APA Hermitian is n. So let's consider the eigenvalue of R. Lambda of R equals to lambda tilde I plus sigma 2 I equals to 1, 2 until n. But for I equals to n plus 1 until m, we have 0 plus 2 sigma 2, so they are only sigma 2. So we have m minus an eigenvalue of matrix R, which are equals to sigma 2, but because the matrix is positive definite, the eigenvalues are positive, so the n eigenvalue of signals are greater than the noise eigenvalues. We call music algorithm as a subspace algorithm. That means the algorithm is based on noise subspace. I mean, we use the eigenvectors corresponding to the noise eigenvalues. If we form the eigenvalues and eigenvectors of R corresponding to I equals to n plus 1 until n, we have R G equals to sigma 2 G. G is eigenvector corresponding to m minus n eigenvalues, G1, G2 until Gm minus n, which is a matrix m by m minus n. These are eigenvectors of R corresponding to sigma 2. I substitute R with A P A Hermitian plus sigma 2 I. We can cancel these terms, and finally we have AP A Hermitian G equals to 0. AP has the rank of n, and A Hermitian G is the linear combination of columns of AP. Because the rank of AP is n, the columns of the AP matrix are independent. So this term has to be 0 because the columns of AP are independent. If I take Hermitian, I have G Hermitian A equals to 0, and this means G Hermitian A omega equals to 0, omega 1 for omega 1, omega 2 until omega n. That means A omega for our frequencies belongs to G null space of G Hermitian. I can make this scalar by multiplying the Hermitian of these. For example, I have A Hermitian omega G multiplied by G Hermitian A omega is still 0. Now this is a scalar, and I can form pseudo-spectrum P omega equals to 1 over A Hermitian omega G Hermitian A omega. I call this pseudo-spectrum, and in real application, because I have the estimate of G, this term for the frequencies is so small, and because I have when this is small, 1 over a small number is a large number, and I have some peaks in our spectrum. That means in each frequency we have peaks, omega 1, omega 2 is the actual location of the peaks are our frequencies. This is the music algorithm. But one may say they should be other frequencies satisfying this equation. I mean, for example, there is omega tilde that satisfies this equation. I mean, a frequency different from our frequencies. But this is not possible. Why? Because, as I said, A omega belongs to null space of G Hermitian. If there is a different frequency in null space of G Hermitian, it means there are n plus 1 independent vector in null space of G Hermitian. That means dimension of null space G Hermitian equals to n plus 1. But this cannot true because dimension of null space G Hermitian equals to m minus rank of the G Hermitian, m minus n, which is n. So there is a contradiction, and we conclude that only the frequencies omega 1, omega 2, and omega n can belong to the null space of G Hermitian. We reached to the end of this video. I hope you enjoyed this video. If you like this video, please press the like button and subscribe my channel. Thank you for your attention.